Hey, we're going to take a look at cell potential for non-standard cells, so non-standard conditions and cell potential, okay? I was just, sorry, I was trying to reflect upon the easiest way to teach this tricky topic. I guess I need to start by sharing my screen. All right, I'm gonna try to wing it again. I usually do best when I wing it. So let's give this a shot, and hopefully this will be the one and only video for this. Okay. We're going to discuss non-standard cells. All right. That is cells with concentrations that are not 1.0 molar. All right. Standard, right? We always do standard, but now we have non-standard, not standard. And we need to predict, I don't know why I wrote the standard right here. We need to be able to, you need to be able to predict and justify your prediction how the non-standard cell will affect the E cell. Okay, will it go up? Will it increase or decrease? Okay, well, guys, let me see if I can make this really simple. Cell voltages, your E cells, are always working towards 0. They are working towards equilibrium, right? At equilibrium, cell stops working. It's kind of like a dead battery, and it would need to be recharged, forced in the reverse direction to build that work power back up. Okay, now, sorry, something just popped up on my screen. It stops working. So that happens at equilibrium. If a non-standard cell, if it takes us further from equilibrium, then E cell will increase, because the cell has been taken further away from where it is dead, and therefore has more work in it, a longer way to go to get to equilibrium. And this whole way, it's producing an electrical voltage. So if this is our equilibrium, and we can take that position away from our equilibrium constant, right? So here's our battery. If we can set up a concentration that moves it further apart, then there's further away for it to go to get dead, and it can do more work. So if the change in the concentration, in fact, takes us further from equilibrium, then E cell will increase, as there is greater work to do in order to get to equilibrium. We've got a further distance to go. If, I don't like the way I'm saying that, if the change, if the non-standard conditions cause us or the system to be closer to its EQ position, and Q is closer to K, then E cell will decrease so that the E cell not standard is less than the E cell standard. And over here, the E cell not standard will be greater than the E cell standard. I hope you can kind of understand why. Maybe if you think about it like this is our non-standard potential, right? Non-standard potential. The potential is created by having this difference in charges and this pull for those electrons, okay? So they're going that way. That potential, I'm trying to reference by the difference. The greater that difference becomes, the more time there is, right? The more charged your battery is, right? The more that can happen before we get to it being dead. This is equilibrium. This is our dead battery, okay? So if my non-standard cell takes me over here, right? Versus here, you see that here my E cell for my non-standard decreases. This is a good little diagram because I only have to get here and then I stop because we're at EQ, all right? But if my non-standard conditions make me all the way over here, then I have that much to go to get to equilibrium before I stop, okay? Now, what kind of conditions are going to take us further from equilibrium, right? Well, this would be conditions further from equilibrium. We're going to see that in that case, we would have lots of reactants and a little bit of products. So Q would be less than K. Simple as that, right? And we're going to see, all right, if we are closer to equilibrium, we're going to have conditions that have placed us closer to equilibrium. Q is still going to be less than K. So it's just going to be not quite as less. So we would see that we have more products. Is that right? Yeah, it is. I'm pretty sure. Let's look up here. Okay, so this is what we're trying to say. Okay, right. Yeah, I was right. I was right. In this case, Q will be greater than 1. Q will be greater than 1. That's what I needed to say. And Q will be less than 1. That's really important. Okay. And at equilibrium, right? Remember that at equilibrium, Q will equal K. Okay. And at equilibrium, K will be greater than 1 because this is spontaneous. So if Q is less than 1, you are naturally further away from equilibrium. If Q is greater than 1, you are naturally closer to equilibrium. Okay? We know equilibrium is somewhere way over here because it's greater than 1, right? But it's a lot greater than 1. Okay? So this is going to cause E cell to increase, and this is going to cause E cell to decrease. Now, I don't know, I've never really quite, I don't know if that worked for you. If it didn't, bring it up. I can talk about it more. We can also look at this, sorry guys, quantitatively. There's something here called the Nernst equation. Right, Nernst equation. And this is our E cell at non-standard conditions. This is our standard E cell, R 8.314, T temperature, in number of moles, F Faraday's constant, natural log of Q. Well, if Q is less than 1 right here, then the natural log of a number less than 1 is a negative number. We will be subtracting a negative, which is adding, and the E cell will in fact go up. If Q, if Q was less than 1, that means we have more reactants and less products. Think about it. The more reactants we have, the more we have to react, the further we are away from equilibrium. Q goes down, we get further over, E cell goes up, okay? In opposition to that, when Q is greater than 1, right? This is Q less than 1, E cell increases. We are further from EQ, right? When Q is greater than 1, we have more products, less reactants. That makes sense. We're getting closer to being done, right? So E cell, we're closer to EQ. There's less to be done to get to equilibrium, and we see that the E cell non-standard decreases. Okay, sorry, let me just use decreases. So we can look at it in terms of the natural log of a number less than 1 is negative, and when you subtract a negative from a negative, it's a positive, and we're adding a positive number to E cell to get non-standard. You could look at it as the natural log of a number that's greater than 1 is a positive number, and when we subtract a positive number from a positive number, we get a smaller number. You could think of it qualitatively, like we tried to do here, okay? But you got to think of it one of those two ways. I think that's all I need to say there. Yeah. See ya. I'm about done.